Okay, so why on earth do we see this in our calculation for the volume of the unit sphere? Where is this rho sign coming from? Now, if you just got out of class, they probably told you something like this. They probably said, oh, so you're going to consider a finite, very, very small element of volume. And I kind of drew, we're gonna think of it like a cube. It's gonna make it a lot easier, rather not a cube, but some sort of box, right? This red side, right? This is all, if we look at the graph in our spherical coordinate system, the red line is going to be our change in rho, our change in distance from the origin. That blue line is going to be some rho, I'll draw it in blue, some rho times some small change in the angle phi or phi. And that's pretty self-explanatory. But then this green line, we have to think again, okay, this is going to be the one that's, this is going to be the line parallel to the xy plane. And so then we have to look at this over here, and we can see that we have some sort of disk that this green is going to traverse along right here, right? And so then we can quickly infer that we'll have, it's going to be r d theta, but then, right, r is not in the spherical coordinate system, so we need to kind of figure out what that is quick. We'll draw a little triangle like this, where we have r, z, phi, and rho. And we can quickly get from some trigonometry that r will equal rho times sine phi. And so then we can go back over here and get rho sine phi. And so then our differential, when we go up to our integral, then becomes a little bit more apparent, right? We'll get this times this times this. So dv will equal rho times rho sine, so rho squared sine phi, and then we have to have times some small change, so d rho, this is also a d, no, that's fine. D rho, d phi, d theta, right? So that's exactly what we should expect when we do it the geometrical way. But there is actually a little bit more of a complicated way of looking at this, and I think that it's very interesting. So what we're actually going to do is we're going to use a Jacobian change variables. So let's quick do that. So we want to go from our Cartesian space to our spherical coordinate space, and we want to be able to do that no matter what coordinate system we're in. So I'm going to write down our coordinate transformations, cosine, and then x will equal rho sine phi cosine theta, and y will equal rho sine phi sine theta. Now, how do I memorize these? I just know that this is r. And I know from Calc 1 or 2 that x is r cosine and y is r sine, right? And so then I'm able to just, if I know that x is r cosine, I know what r is from this triangle, then I can quickly develop those formulas. Okay, so if you've done Jacobian transformations, at least at my university, you've only done it in 2 dimensions. But this is fine. This should feel like a perfectly natural extension to that thought process. So I'm going to say that my u is equal to rho. My v is going to be equal to phi. And my, in this case, we have a 3rd dimension, so we have w equal to theta. And so we have to develop the Jacobian matrix. So our Jacobian matrix, we actually are going to take the determinant of the Jacobian matrix. So I'm going to write J rho phi theta. This will equal the determinant of the Jacobian matrix. which if you remember, the two-dimensional one is when we do partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. That's our 2D case. And then when I write out the three-dimensional case, this should feel pretty logical. So we have partial x, partial rho, and then we'll do dy d rho. I'm going to say d because it's quicker. And then we have dz d rho. And that's the rho variable, right? Then we just go to the next column, and we have dx d, and let's do phi. And then we have dy d phi, and dz d phi. D phi. All right, and then our last one, our last column is dx d theta, dy d theta, and dz d theta. Okay, so if we take the determinant of that, that's going to be a lot of things to do in one step. So let's just get an equivalent expression where we actually show what those are equal to. So we'll have a identical matrix, and our first entry are, let's scoot this down so we can see it a little better while we're writing this. Okay, so we need to get x with respect to rho. That's going to be, and this is a part where you have to be very careful, because if you make a mistake in this step, you will pay for it in the algebra, because it will not work out, obviously, because you made a mistake. That's how mistakes work. Okay, so our first one is going to be sine phi cosine theta, right? All of the ones in this column, we're basically just going to get rid of the rho, right? Because that's how partial derivatives work. And then our next one is going to be sine phi sine theta. And then our last entry in this column will be cosine phi. Okay, let's scoot this down a little bit. Okay, and then the next thing we're going to do is the next column. So we'll have rho cosine phi cosine theta, and then we'll have rho cosine phi sine theta, and then here we will just have minus rho sine theta, or sine phi, my bad. And then in our last entry, we have minus rho sine phi times the sine of theta, and then we have rho sine of phi times the cosine of theta, and then z, if we look over here, z does actually not contain a theta, so its derivative with respect to theta is 0. Okay, so we're going to take the determinant of this. It's going to be a pain, but we're just going to do it. Okay, so this will be equal to, we write for the first part, we do this times this minus this. So let's do that. So we'll have cosine theta times something times 0 minus a minus, so we have plus rho squared sine squared phi cosine theta. Okay, that's our first column in the determinant. Now we'll do this. The way I like to write it is with a minus sign in the next part. So I do minus this times this minus this. If you don't know what I mean by this, it means I'm multiplying the diagonal, right? If we're watching this video, you should probably have learned how to do a cross product by now. I guess I didn't really think about that. Okay, so we're going to do minus rho cosine phi cosine theta times something times 0 minus rho sine phi cosine theta. Don't worry about that. It looks weird, but I promise it works out in the end. And then our last part, we're going to take this times this minus this, and we will get sine phi sine theta times what do we have? We have minus rho sine squared phi times sine of theta. Is that what we have? Yes, and then we have another component here, and it's going to be rho cosine squared of phi sine theta. And hopefully you've seen some patterns start to show up. We have lots of sines and sine squareds and cosine squareds. It means we're probably going to get some cancellations here, because obviously we were looking for, right, we're looking for this. We just want this, right? That's all we want, and there is a lot of stuff here. There is a lot of stuff here, and I guarantee you it's all going to cancel, and it's actually really cool. Okay, let's finish this. So we have, let's simplify, let's expand, well, rather we're going to unsimplify. We're going to kind of expand everything into what it's going to be. So we're going to have rho squared times sine cubed of phi times cosine squared of theta. Right, I'm just going left to right up here if you're not following my thought process. And then we have plus rho squared. And then this is a lot of stuff, but it's going to be, we have sine phi, and then we have cosine squared of phi, and then we have cosine squared of theta. There's lots of cosines there. And then our next term is going to be this term. So we have plus rho squared sine, is it sine? Should be sine, did I make a mistake? Sine. Oh, yes, okay. So inside of the simplification, so inside the equation, we're actually going to take a look at this, and we're going to, let's analyze this for a second. I have minus rho times sine theta times sine squared phi plus cosine squared phi. And so we all remember that this is equal to 1, and so this guy is equal to minus rho sine theta. Okay, so that was the, it becomes a little bit more difficult if we don't do that from the get-go. So let's simplify that. So we have minus rho sine phi sine theta times minus rho sine theta. Okay, let's continue to simplify. We'll just copy this row and finish that last operation. Let's finish this. So we're going to have plus rho squared, and then we're going to have sine of phi sine squared theta. So if you're like me, you're already seeing lots of rho squared signs, which is good. So our next step is going to be to factor that out. We unfortunately are not doing this in the most good-spirited fashion, right? We already know the answer, and so we're looking for it. And so that's kind of going to take away from the magic of this problem a little bit. But we have rho squared sine of phi. And then we know that this has to be rho squared sine phi. So whatever we multiply this by, it's got to be equal to 1. So we should probably factor it out. So if we factor this out, we get rho squared sine phi times the quantity sine squared phi, right? Because we had sine cubed, and then we took out a sine, and then we have cosine squared theta, and then we add cosine squared theta time, is it theta? Yes, and cosine squared theta, and then we add this is sine squared up there, my bad, plus sine squared of theta. Okay, and then we have exactly 2 more groupings left before we can get to 1. So we have rho squared sine phi times, and then let's do a grouping here. So I'm going to factor out a cosine squared. So I have cosine squared of theta times sine squared phi plus, you see what's happening here, right? Cosine squared phi plus sine squared theta, right? This is equal to 1. So we're left with rho squared sine phi times cosine squared theta. That sign looks weird, right? Sine squared theta, which is equal to, again, right, this guy's equal to 1. And so we're equal to rho squared. All right, so that is how we are able to arrive at the change in differential for the spherical coordinate integral. Yeah, thank you for watching.